All right, thanks, Paul. I think Paul did a good job giving an overview of kind of the how and the what and the why and where of the batched code. But I'm going to be giving a little deeper dive on the how-to side. There have been some changes that are user-facing, right, that show up in the input file to QMCPACK, as well as to the main workflow automation system that drives it, which is NEXUS. So I'd like to lay those a little bit side by side for everyone. I know that's not going to be of a keen interest to everyone, but for those of you who run the code regularly, I think you'll appreciate these differences because a little tedium now is better than a lot of tedium later in missing out on any of these jumps and differences. Okay, so overview of what I'm going to share. So first of all, I'd like to give a bit of an overview of example files on the GitHub site that are up and ready that you can run right now. So again, if this talk gets a little dry, mosey over to the GitHub site, download it, try running the examples for yourself. Okay, and that's what I would advise. So I'll go over the example files. I'll share a bunch of examples of legacy versus batched inputs for QMCPACK, so the changes in the XML and also the changes in the NEXUS, which is represented in Python for common use cases. So what are those? Variational Monte Carlo, variance minimization for optimization, energy minimization, what a diffusion Monte Carlo run looks like, physical observables, how you specify those that are available in the batch code. And finally, so that's all CPU focused. So that's just saying, okay, this is how you've done it in the past on CPUs. This is how you can do it now to reproduce exactly what you've done in the past, your prior practice. And then a very small example on running VMC on GPUs with some emphasis on working within the memory limits that Paul also mentioned were important. Okay. So on GitHub, so if you have the link, you can mosey over to the main QMCPACK GitHub. Underneath the main QMCPACK GitHub is the link for this workshop. And inside of there is day one NEXUS batched. Inside of there, you'll see a bunch of files. These are a bunch of Python files. Anything that says diamond whatever batch.py, that's a workflow for one of those particular examples that I mentioned. There's also a README there posted. So if you go to the website, you're greeted with this README. It will give you a description of the files. This is a very simple example. This is just a primitive cell of diamond using BFD pseudopotentials with plane wave derived orbitals from DFT and a two-body Jastrow factor. And you can run all the different types of examples there. The only requirements that you're going to need is that you have a working install of QMCPACK and NEXUS. But these aren't full workflow examples. We're not running the DFT and then the optimization and then the final run. I've set it up so that we can run NEXUS in a mode where the wave function is pre-existing, the Jastrow is pre-existing. You can just run QMC. So if you can install QMCPACK on your laptop or machine, you can go and do these examples right now. Okay. All right. So again, this is where the main workshop site is listed. In order to get things up and running, you either do a git clone or wget one of these links. For those of you who don't want to read the README, again, it's just git clone, go into the workshop, you edit this one particular file. All you need is to set your path to your Python your QMCPACK executable, right? That's the minimum you need. It needs to know where QMCPACK is, and then you can run the example. Okay. All right, so prior materials on NEXUS, for those of you who aren't familiar with using NEXUS before, this is not an in-depth tutorial from the top to bottom of doing QMC or running NEXUS, but that type of information is available. So if that's what you need and are interested in, please go and check the NEXUS manual. You can refer to the original paper. The 2021 workshop had a lot of top to bottom examples of running the workflows, so I include those links here. Particularly this week 3 stats in NEXUS has a full README PDF walkthrough tutorial that you can go through. And as a reminder, installing NEXUS is really fast. You just clone the QMCPACK repo. You point at your Python path and your path at two destinations within that repository in your bash RC, and it will work. Okay, as long as you have a decent Python 3 and NumPy installed. Okay, so with that, I'm going to roll forward through the different examples and what they look like. So again, if you want to go run the examples now, please do. Otherwise, pay attention to the differences. So what does VMC look like in the input file? Okay, so on all of these, legacy is on the left and batch is on the right. And as Paul mentioned, one of these new parameters is the driver version. If you specify legacy, you get the old drivers. If you specify batched, you get the new drivers. Okay, so in every build of QMCPACK that you do currently on CPU, both drivers are available. So if you have a QMCPACK build, it can run legacy and it can run batched right now. Okay, so for variational Monte Carlo, beyond just specifying driver version, what's the change? Well, this Walker parameter is no longer supported. And what I would recommend is to simply specify nothing in the input file on the right. What that will do is it will essentially set one Walker per thread, so per CPU core, and populate VMC that way. That's usually the way you want to run. That's the simple thing. So by default, you'll be doing the right thing. So simple enough there. All right, in NEXUS, this also looks pretty simple. So I gave kind of a snippet of the input file here. This is the totality of what you specify in NEXUS. So just for those of you unfamiliar, you can point it to the orbital file. You can point it to the JASTRO file. So if you have pre-existing orbitals or JASTROs, you can read those in and work with them. You don't have to do the full workflow. In legacy, this is how you specify that exact input file on the prior page, this number of blocks, that number of steps. On the right, the only change is to tell it the driver version, which is batched. Okay, so for the simplest of things, you only need the simplest of changes, and you should be able to go forward and be good. All right. For variance optimization, somewhat similar. Again, you have the driver version, which you change. There are some changes in how you specify the optimization. Okay, so this is variance minimization done with the Quartic optimizer. You can handle a cost function, but somewhere between variance and energy, right? And originally, in the legacy driver, you could specify the number of samples. So in this case, about 51,000 samples. That's the total amount of work you want the code to collect and do the optimization with. In the new code, there's some discussion about how to handle the total amount of work in a unified way, between VMC, DMC, and optimization. For the moment, that's hanging. And so the number of samples that are created is actually the product of the number of MPI ranks multiplied by the number of threads times the number of blocks and steps. So you have to do a one step of arithmetic if you want to get the an exact target number of samples, right? So you specify some number of blocks like 200, and you can calculate from that the number of steps if you have a number of samples. That's why it has this odd number 22, is to try and get exactly this 512. But of course, if you don't care that you want exactly 51,000 samples and you're fine with getting more than that, right? This input on the right, if you ran on more nodes, would simply produce more samples in the optimization. And for many cases, that's fine. You just want to use the available work that you have. Okay, in NEXUS, what's that look like? Okay, so of course, before you specify the number of samples, over here, here's just showing that you can do that little bit of arithmetic within NEXUS to get the 51,000 samples that you want in terms of blocks and steps. Okay, one little note is that this is inside this loop. This is 6 iterations of optimization. You specify that with this cycles parameter here, and it will generate 6 cycles of optimization. Okay. How about energy minimization? So that one's just slightly more complicated. We're using a different optimizer. This is the one shift only optimizer, the one that's recommended for energy minimization. And you'll see it recommended to be done in two stages. So a few iterations with one approach and more iterations with another. The change is in this min Walker's parameter. That's kind of a tightness of how far you're allowed to change the wave function. It's measuring like the wave function overlap or the ratio values. This is a much looser control for a while you have a poor wave function, and then a tighter control later. That's essentially why you have 2 blocks. But the change is exactly the same. Apart from the driver version, samples just gets absorbed into blocks and steps just as before. And in the NEXUS input, it's exactly the same as that, with the change being just specifying blocks and steps. With energy minimization, again, the change here in NEXUS is to specify one shift optimizer as the minimization method, and then how many initial cycles you want with the looser control and how many cycles you want with the finer control. Okay. If there are any quick questions, I'll take them. Otherwise, I can go forward with the diffusion Monte Carlo. Okay, no, I don't think there's anything complicated here. So this is mostly informational. All right, so DMC, what does DMC look like? Okay, so in QMCPACK XML, again, very similar with the legacy and batch driver change. So in Diffusion Monte Carlo, in the legacy driver, you would specify that you had a VMC section running with, say, one walker on each core, and it was to collect a certain number of samples, in this case, 1,000 samples. That would then become the total population in DMC. So DMC operates usually on a larger walker population. It has a target that it fluctuates around, keeping that fixed. That's how it was specified there. In the new drivers, you can use the total walkers parameter, but instead of just specifying it in one place, like the VMC, you have to specify it in every single place. So that's a change, just to note, that's the way it is. Your VMC will be done with the number of walkers that DMC needs. In CPU, you can see why it was convenient to do it this way. If you're doing it on either CPU or GPU, you can see in GPU, it might be better to do it this way. Have a full occupation of the GPU, right? With the full population, and then just hand that population off into DMC. And so that was kind of a compromise in between the two for that. But again, just a small change, but you do have to note that this is needed in each place. So don't get caught off guard by that. All right. In NEXUS, again, the changes are fairly small. This was a 3-section run. Okay, so this was VMC followed by Diffusion Monte Carlo with a large time step to equilibrate rapidly, followed by a production run at a smaller time step. So in NEXUS, you can split that as well with the VMC, the equilibration DMC, and the main DMC. The only change is going between the samples here that you specify here to total walkers. And in NEXUS, unlike QMCPACK, you specify it in one place, and it will just put it there everywhere for you. Okay. So again, if you're doing in NEXUS, you're going to see even smaller changes than in QMCPACK most of the time. The possible exception is in estimators, which are still, I'd say, undergoing some development and in some motion. So if you have opinions on how it should look, A, or B, some observables that you want to see that you don't see here, be vocal. That's the kind of feedback we'd like to have. So, okay, so how do we get physical observables? All right, so this is getting a little busier on the left here. I've tried to keep it a little more condensed, but the part you're supposed to focus on is in this Hamiltonian section. So this is where all estimators could be specified in the past in the input. So you had intermingled things like the Coulomb potentials and the pseudopotentials, and then what physical observables you would measure. And on the left, I'm showing even a superset, a slight superset of the observables supported by the batch drivers. So what have we got? We've got the modified periodic Coulomb, the Chiesa kinetic energy correction that's actually not supported in batch, but it formed a part of the key finite size corrections originally, so I kept it here. And then more typical observables, there are 3, right? There's the spin density, the momentum distribution, and the one-body density matrix. In each case, this is how you specify them. In black, I'm highlighting places where there's going to be a change. Okay, so in this case, the Chiesa estimator is not supported. Here, for the momentum distribution and the density matrix, there's actually a type change that reflects it. It's actually kind of more of an internal developer issue because there was a separate class which had to be implemented for each of these, very specialized for the GPU. So it was kept separate. It has a different name. So that actually is a change that's reflected in the input file. It's not a big change, but it actually is an important one. And the other thing is that is where the information is located. So how I've arranged this, it looks very similar, but you'll notice this introduction of a new block, this estimators block. So instead of everything being jammed and puddled together with the Hamiltonian, all the physical observables are now bundled in this estimators block. Not a big change, but it does have to be there. So please keep that in mind. As before, I don't know if anyone ran this way before, but you can also specify the estimators one by one in each method section below. For VMC or DMC, if you just want to measure it in DMC, you can put it there. That works exactly the same in the legacy drivers and the batch drivers. Okay. In NEXUS, again, that change is reflected. Basically, that's again, these names get propagated, whether it's momentum versus momentum distribution, DM1B for one body density matrix versus actually spelled out with all the words lengthily. But that's it. All you do is specify that slightly different name and give it the batch driver, and you'll be off to the races. So there's one example like this. If you haven't worked with all these observables before, go ahead and have a look at that example on the GitHub. Go ahead and run it, both legacy and in the batch drivers. Take a look. Most of the information that comes out is in the stat.h5 file because it's heavier information. It's an HDF5. Okay. Finally, just a quick note on GPU offload. So all those examples before were just on CPU. So if you how to translate your old CPU runs into current CPU runs. All right. So as Paul mentioned, on the GPUs, one thing that you've got to be concerned about is really how many walkers per GPU you've got, or this batch size. So typically you're running in a configuration, and actually QMCPACK only supports one GPU per MPI rank. And so a natural parameter to use is walkers per rank. That actually you can think of it in your head as being walkers per GPU. So that's, and when you're running there, what you need to be able to do is to saturate the GPU to the extent that you can. So if you run it with only one or two walkers, you're going to have a significant amount of the processing power going to waste. That's not what you want. On the other hand, if you just say, give me 10,000 walkers, you're going to run out of memory and the code will fall over. And so at the moment, we'd like to have something more automated in the future, but for the moment, you actually will scan over a collection of different numbers of walkers and monitor the run and essentially see what fits on your particular flavor of GPU. I'm showing how you can do that in NEXUS. This is actually just a compact for loop. This will generate a bunch of VMC sections end to end in the input file and all with their separate data. That's what I'm showing on the right is just the number of different walkers per rank that will be created by that. And you should monitor A, that the run completes, and B, that you're getting the kind of throughput that you want. C, probably if you're advancing enough steps in time to equilibrate, right? You're going to want a certain number of equilibration periods in your run so that your statistics coming out the other end are meaningful. But this is, but by going through this simple scan, you can kind of monitor that process and get a sense for yourself how that works. I'm not going to explain in detail, but a couple of parameters that are particularly important for the batched version for performance, and possibly Ye will talk about some of these in a minute. One is delay rank. That's how often the inverse matrix gets updated in the random walk. That's a heavy step, typically order n to the cubed. And so if you can postpone that a bit, you can gain some savings. That batch has to do with batching the determinate updates themselves. And finally, this crowds parameter is here. And again, I'm not going to elaborate in any detail, but I'm just showing you where you can specify it. And again, that's a little different on a GPU than on CPU. Okay. With that, I'll take any questions if there are any. And it was fairly straightforward, I think. But if you have questions, please ask.
I just wanted to ask about your previous slide when you talked about kind of monitoring this scan. What, as you do this, what is NEXUS going to report? I mean, like if I do something like this, I expect, is it that I expect at some point the machine will complain or I've run out of memory? And then in that case, what will NEXUS report?
Okay, that's a good point. So NEXUS in this case is actually simply generating an input file for you and submitting the job for QMCPACK. So QMCPACK will be performing the run. And what you'll see is that QMCPACK will generate a set of inputs for each of these sets of walkers per rank, right? You'll see a different series of scalar.dat and stat.h5 files appearing. If you happen to run out of memory, you'll probably see an out of memory error in your either in your .error file. And that's where it will appear. If you didn't, all the data will be there. The run will complete successfully. And then you'll just be up to you to analyze the data. You know, in the scalar.dat file, it tells you how many seconds were spent on each block and so forth. And so you can see kind of what your performance is from that.
Actually, just a comment about this scanning. this is something that ideally one only needs to do sort of once at the beginning of a project. For example, let's pretend we're going to study some 2D boron nitride, right? We're going to make a supercell with 100 atoms in it, 400 electrons, and we're going to do this scan. Let's suppose we find out that for our Intel GPUs, we need 1,000 Walkers. Let's suppose, right? That fits and it gets the 90% of the performance. We're happy with that. If we then do a supercell with 99 atoms because we made a vacancy or one more, right? It's going to be the same batch size is going to be good, right? Because it's about the same amount of work. So yes, this is an initial step, but once one starts running on a particular computer and doing a certain class of investigation, we're hoping that everyone will get a feel for what this is. So it's not too much extra work, but it definitely is extra work, and we would like to automate it long term. But this is where we are right now.
And I'll just one comment to that. So this is a per node kind of quantity, right? This behavior is replicated on every node. And so if you're on a big HPC machine, this is something you run on just one node quickly, maybe in a debug queue, something like that. You'll notice that I'm only taking, just a few blocks, a few steps. It's very short, very rapid. So just run on a single node, do your measurement, see what you need. Then subsequently after that, you're going to run in production with the number you choose on a lot of nodes. Okay, so this should be a quick step. We are hoping to automate it away in the future, but that's currently what you have to do.
Sorry if I missed this, but can you explain what dead batch does?
So that's a determinant batching. I think probably Ye is in our best position to explain in detail what that does.
Yeah.
I don't know if that's part of your talk, Ye, but
So in the beginning for the CPU implementation, everything's done a worker at a time. It's when we implement delay update, everything is one worker at a time. That means some worker get accept, some worker get reject. So now we need to submit work to the GPU. So we kind of want to mandate lockstep advancing. So the algorithm has to change to cope with the reject moves as a fake accept move. So there's a lot of internal kind of algorithm divergence in implementing all the APIs interacting with the determinant class. So your calculate ratio can be different. The calculation of accept reject move can be different. So in the end, we decide it's separate class in the implementation, and you're basically selecting which class you're using from the input file. Oh, Paul was asking, should it be always set to true? My recommendation is technically you can leave it blank. If you build it in just CPU build, default is not batched, the optimal CPU code. If you build it with GPU, the default is batched. But you can override it because the logic of new code is you can override at runtime, select the other side of features. Yeah,